So anyway, so as I said, this sliding windows was popular for I guess from mid-90s, 1990s, all the way until even now, you can say it's possibly used, for example, in algorithms like YOLO, even though you don't scan exhaustively. So it would be a very simple idea where you just scan and then you try to detect. And possibly this Viola-Jone is more or less the same idea still, but it's the algorithm is much refined. So of course, the early challenge is still a challenge. Is that you have high resolution, especially when you now goes into videos that get higher and higher resolution, for example 4K, and you just have many of these small windows if you want to look for faces in the image, and also the things you're trying to detect is not so actually common, or it's relatively rare. So maybe 0 or to 10 faces per images typically. So we just want to have something pretty efficient, right? So this is kind of a summary page for some of these influential algorithms and works in terms of detection. So we won't talk about things earlier than here. So but we'll talk about Viola-Jone, and we probably will talk about dielectrics next time. And Gersic works. We probably talk about at the end of this class. I mean not this class. I mean the final week maybe. So basically, Viola-Jone, as I mentioned, is kind of still a sliding windows approach, and it's kind of pretty seminal work. It's before that, there's some algorithms, but are typically pretty slow, not real time. But this one is kind of more or less at that time you are using 2004 computers, and you can still make it kind of real time, and detection accuracy is kind of decent. And basically the key idea is trying to kind of use some kind of very weak classifier that is pretty quick, super quick for detection. Then it's trying to combine them together. This is the typical boosting idea. I'm not sure. Actually, anyone know boosting? Anyone heard of boosting? Anyone took a class in machine learning? There's any machine learning class in this university, do you know? I think there's a couple, I don't know, maybe in computer science. So anyway, we would mention a little bit the idea of boosting. And then that the third one we'll go into detail also. So first of all, the idea, the classifier themselves, or you can think of them, the features themselves, is really simple. What the features they use is simply just this kind of rectangular filters. So it's you have a very simple filters. It's even simpler than convolution. So you just have on this darker side is all -1, and this side will be +1. And this just give an example. Let's say you have an image, you have a filter like this, you just have this filter scanning over the entire image, and then you have another filters like this, and another filter like this, and so on. So because this filter is so simple, then computing this filter essentially is just trying to sum over all the pixels in the white area minus all the pixels in the black area, right? So it's kind of extremely simple filter. So this is a demonstration. Let's say I have an image like this. I expect like, okay, this give me a threshold that like going through this filter is a good result, or like something like appears to be a candidate of a face, and this is not. So very simple. Then of course the difficulty here is like how do you compute this efficiently? And first of all, like it doesn't look like this will be like a good candidate, right? Therefore, like it won't work if you just have one of these filters. Basically, you have like thousands, millions of these filters, and in practice, you chose from millions of them. You pick 1,000 of them that you think is good, and you combine them together and give you a good face detector. And before that, like let's look at like how to, let's say, compute them like efficiently. So as I mentioned, like, you have many of those, right? So you have like in that case, it didn't go up to 1 million, but in the original paper it says like 160 like thousands of them. So we just try all these different combinations over areas of just 24 by 24. That's kind of like for the detection region they pick. And so to compute this filter like efficiently, the authors make an ingenious like observation. Basically, what you're doing is simply kind of like summing over an area like a block, a rectangle of pixel values, right? Because I sum over part and then I subtract over another part. That's basically what the filter does. So then it just need to find a way to very efficiently computing summing over values over a region of the image. So, and what they did is they think of it this way. They first compute a so-called integral image. So you have the image, original image, you just like end them up kind of like, basically you have this integral value, like from the original image, you convert that into like some integral image that like the integral, if I kind of extract the integral, the value of this integral image at a particular pixel, let's say at this pixel, it basically equal to the value of the sum of all the pixels in this rectangular block of the original image, basically for all the pixels above and at the left-hand side of, all the values, pixel values on the above and the left-hand side of the original image. And of course, this can be computed pretty quick. So actually, in MATLAB, you can compute that with just just one line to this QSum commands here, and you will be able to compute that really quickly. And with that, so is that clear? No question here. So with that, we can then like compute the sum of all the values inside the rectangle using this integral image. So it will be simply like that, right? So if let's say I have any region, I want to sum over that with this corner like A, B, C, D here. So the sum will be just equal to, will be equal to this rectangle plus this rectangle minus this one and minus this one, right? Does it make sense to you? So because this one plus this one minus this one will give us this one, right? So and this minus this will be this one, right? So therefore we have this simple equation here. And of course, like all this area, for example, this one, this one, this one, and this one, all of them can be just retrieved from this integral image that we computed earlier. So therefore, like this will be like super efficient. So this just repeating what I said, like anyway. So then we have all these features that we can compute efficiently. Then now we need to decide like how to combine them. We should not just like arbitrarily combine them, right? So this comes from basically we utilize the idea of boosting I just mentioned earlier. The idea is that like you start with like a lot of like pretty weak classifiers, and you're trying to combine them like kind of intelligently so that like you can create a strong classifier. So here's the idea. Basically, let's say you have some starting training data here, and we try to decide which classifier. Let's say just give a very simple example here. We have, let's say the weak classifier is just a linear classifier that's trying to draw a line here to separate the data set here. So let's say, and let's say after some training, this is the best classifier we find for this example. And then like we have this first weak classifier that we have determined. And then like afterward, like for all the errors, error cases, we just boost these error cases to have like larger weight. So that's why we call this boosting. So we just make those, like these are the error cases, right? Because all this side is supposed to be red, but these two data points here is like misidentified. And also this is like misclassified. So we just kind of like make them have a larger weights. And then after we have make it a larger weights, we have like kind of like essentially a small difference. Like kind of you can think of a different data sets now. Then we can train again with the same procedure, right? And identify a second like weak classifier. And let's say this is the second weak classifier. And again, we'll do the same thing, right? So for those, it's actually considered as it's misclassified. We just boost the weight of those data points again. So we just repeat this step. So we create we have trained several like this kind of weak classifiers, and then we can combine them like by just based on like the accuracy of this weak classifier. So for more detail, you can just look into this paper, like, or like you can just search on Wikipedia or YouTube videos like on edibles and boosting, and this is a pretty standard approach in machine learning. So with that, we can now train the model, right? So we will start with like all this combination of filters. It's just this very simple, this kind of filters. I'm trying to see like which one gives us best result, like amount of this data here. And then like it turns out like this kind of interesting, like actually just these two filters here after training will give us like 100% recall, but like only 50% precision. That means that like we can, if we just use these two filters, we will detect all the possible phases, at least for the training set there. But like half of the times you'll get like something long phase, like and kind of misclassified as phases. So this just get into a little bit more detail, repeating what I said here. So we have HJ here is the weak classifier, and the weak classifier in this case, the only parameters we have is like the actual location will be the features, like basically the several different corners that you determine is black or white, and then like we have the threshold there, like determines like based on this filter whether it's bigger than something, or okay, this is the threshold like theta j here. If it's smaller than these values, then the output for this classifier will be minus sj. Otherwise, it's plus sj. Okay, sj here will be just plus or minus 1, and whether it's plus or minus 1 will be determined by this polarity here. And then basically we just need to come up with the appropriate parameters for this weak learner for our data set. And once we have that, then we'll go for the boosting, right? Then we'll just pass the data through this weak classifier, identify all these errors cases, and then boost the weights there, and then train this again to build another weak learner, and so on and so forth. And yeah, that's so. So the advantage, this is just a summary of advantage boosting and SVM. Like, of course, both are actually very popular machine learning techniques. I would say like deep learning, and still like very useful. I would say methods, and so for boosting, some of the issues here is like. Okay, some of the advantages kind of like similar to deep learning in the sense that you can incorporate some of this feature selection into the training algorithm there. And testing, actually, you can make it very fast. And there's some flexibility to construct your overall classifier as well, because essentially, as you can see, it's kind of multi-stages in nature, right? Because you build a number of reclassifier, and you can terminate anywhere. Right? I will give more example afterward, but you have a bunch of reclassifier. Let's say the first one, you say is a phase, and then like you can have the second stage like reclassifier to further say, okay, I have this phase candidates. Can you make sure that it's really a phase or not a phase? Right? You can go like multi stages like that. So therefore, like, you can build classifier pretty easily to make it like increase the precision and so on. And you can also trade off like computational complexity when you are doing testing very easily also. And disadvantage is like it's actually pretty slow in terms of training, and typically needs more training samples like than SVM. And in terms of like pure performance, usually it does not train as well as SVM. But it's fast because okay, training is slow, but testing is really fast, as I just mentioned. Like this slide illustrate better like what I just said. Like you can have multiple stages, right? Remember, like each of these those weak learner here, you have this threshold here. So when you have a phase or new image coming in, you go through the first stage. If everything is rejected, you can just stop here, right? So if you don't find a phase, you just stop. You don't spend any more computational cost here. And if you find a phase, you can refine your accuracy there, like to say in the second stage whether it's a phase or not a phase. If it's not a phase, again you stop there, right? No more compute. So therefore, like it can be very fast in practice. And yeah, that's just again repeating what I said, right? So you can stop everywhere, anywhere, and then like you can just keep cascading to improve your kind of accuracy there. Like your precision at the beginning is kind of low because you basically accept lots of long phase as phase, right? But as you go to another stage, you can reject more like long phase, and then you can increase your precision. Let's see. Yeah, actually, this is just repeating what I said, so I guess I will just skip that. This is kind of like some detail they used like in the experiment at that time. They have 5,000 phases, like all of them like kind of scaled down to like just 24 by 24 pixels, and then like they have also like lots of long phases, like 300 millions of them. And they try to include like many variations, like across individuals, like enumeration, polls, and so on. And ultimately, they create a classifier with like 38 different stages, and each of the stage they have like various number of features. So they, in the sense that it's not just one reclassifier there. So each stage it can have multiple reclassifiers there. Oh, okay. Yeah, maybe, this is other details. You can just read that, but maybe I just emphasize here a little bit. So since like we fixed the size to be 24 by 24, if we don't do some rescaling, then it can only detect very tiny faces, right? So what they do, of course, you can scale the image itself to for example, like just use the pyramid as we discussed like earlier to solve the scaling issue. But remember that like we computing these features is really quick. So therefore, like it's actually more efficient rather than scaling the image. You scale the detector. You just like make the detector bigger, right? Because each of the detector, once you compute the integral image, each detector just call out 4 values and 3 additional subtraction, right? So it's super quick. So therefore, they just try to have like different scale values. Typically, like you have scale step is 1.25, and then you scale several times. And also they include this long maximum suppression. Basically, if you have a face here, maybe you have like several boxes appears to be face, right? Then you want to like just summarize one box there. So this is called long maximum suppression. Typically, it's just like kind of like average out the overlap. Let's say you have your 2 boxes here, like that kind of overlap, have significant overlap in here. So you expect that both boxes is basically correspond to the same target. So then you can just like average out the coordinate, right? Basically take the average of these 2 coordinates, average of these 2, average of these 2, so on and so forth, to get the final box there. And they also like train like multiple classifiers. Like they have this many stages of like final classifiers, right? So it's big classifier, but they train 3 of them just to further increase the accuracy, and then afterward they just take votes. So basically, like, if like 2 of them say it's a face, then they consider it as face, so on. So at that time, of course, it's kind of dated. Like at that time, they have a sun station there, and when they train it, it takes weeks to do that. And as I mentioned, I have like this 38 cascade, whatever. And they have a really slow computer for testing, right? It's like 700 megahertz, like Pentium 3. But it still can go real time, like almost real time at that time. Like it's like 15 hertz, like 50 frames per second. So of course now it's totally real time, right? So you have this is like some of these results here. It's kind of decent actually. This is like this false positive, false negative, and so on. And of course now you can just pull it out from OpenCV and let's see. For example, compile a tiny code here just to do that. In OpenCV you can just they already have the train model there. You can just pull it out like in OpenCV, and it is only detect grayscale image, so you need to convert to grayscale first. And the code is really simple, right? So I can just test. Okay, that's myself. Oh wait a sec, it doesn't work. Okay, it doesn't work with a cap. So let's try. Okay, anyone? Oh shoot. Take the. It's this side. So anyone want to get into the screen? Just try one more face. But you will be on YouTube, by the way. So if not, it's okay. Like anyone is okay. Joe, do you mind to be on YouTube? Let me try on you. I don't know. But it's okay. Okay, it can't work. Yeah. So it's kind of like at least like you don't like 2 faces is okay. Yeah. Sometimes it's but it's decent actually. And of course it's super fast. And this is kind of Viola-Jone's. Even though it's kind of dated, like actually it's okay for most applications. Like if you have like tiny projects that just want to put it out quickly, that doesn't need to be like really high accuracy. Actually, it's something kind of decent. Okay, this is just a summary that is basically doing sliding window with this feature is just this really simple kind of filter, and then use boosting and so on. Of course, I guess like the most ingenious part is the implementation, right? Because all this idea is not, this kind of simple highlight filter is not new, and then boosting is not new, but the implementation at that time is really kind of like ingenious, and then make it possible to make it real time. So that therefore like people were so excited about that at that time. And then I use up like about half of the time. So let's talk about face recognition. I like to talk about a couple algorithms today. So the other one I like to talk about is Eigenface. It's used for face recognition. Of course, like this, just to make sure that the take-home message you can, at least you know that face detection is referring to, and face recognition referring to different things. So typically when we say face recognition, we actually want to identify the person of that face there. So let's say I don't want to recognize this girl, let's say Nicole, or maybe even the gender, like age and so on. Typically it's like the identity, not so much the gender. I guess the gender will be kind of analytic, that kind of stuff. So this more face recognition, just usage. Of course, I don't think I need much introduction now, as this is all you are using it every day, right? For example, we use Facebook or like Google Photos and so on. They already have this face recognition and can group all the faces together. Then all this application you're using it, like even without like realizing that, like. And of course, like surveillance is a big thing, right? And I don't know, it's like kind of horrible things also, I think. In Asia, it's really popular, right? To say, okay, that thing I really in doubt, right? Even though like in China or like in Singapore, they say like you can like have like accurate recognition like 1 out of a million. I really don't know how. Really, I think like you have two faces, like 1 out of millions. You find two persons is like look quite similar to each other. It's really easy, right? I don't know how they can have like maybe 99.999 like accuracy and so on. But anyway, like I guess in terms of this more relaxed application, let's say just for album organization or maybe just I guess I mentioned one of this application like maybe earlier. This is kind of VIP applications. I'm not sure I mentioned that before. Like for example, like you have a clubhouse or like a very kind of luxury kind of residential place that you have this guard like just all the reception there, like just try to greet you appropriately. You have like 1,000 guests, like you probably cannot remember everyone, right? So you can have this cheat sheet monitor, like just identify this guy is what, and then address that person like correctly. And for those applications, you can afford to have like, and also you probably only have 1,000 people instead of a million people. And of course, 1 million people, if you were talking about what you want to like catch everyone like correctly, would be what 7.9 accuracy, like 6.9. I don't know how to count anyway. So those is not very realistic. So but anyway, like let's talk about the algorithm itself. It's also like it's not very new algorithm, but this kind of approach was used like pretty often. So okay, first of all, think of like all images. Of course, I guess we mentioned it several times already. Like if you think of the image space is huge, and within this image space, like even within the lateral image space of lateral images, among those, for those like to be considered as face is even much tinier, right? So and for example, here an example you have just 100 by 100 like pixel images. We can recognize right away like what is considered as face, what are not considered as face, and and to do a good recognition of face, the idea for Eigenface is that we want to first identify the space of faces in the image space, and of course, you have the high dimensional space to start with, right? Let's say, again, you have this 100 by 100 images, so it's 1,000 or 10,000 dimensional space. Now, what we want to do is we want to do a reduction of this dimension. So it's actually really standard things, like in machine learning, statistics, everywhere, is that you have a high dimensional features, and now you reduce to the lower dimensions. And okay, actually, it's a really standard thing. So anyone can tell me like what we should do for that. We basically have like a high dimensional data signal or high dimensional features. In this case, it's 10,000 dimensions. And we cannot manage to process in 10,000 dimensions. So let's say we want to shrink this 10,000 dimensional space into like just maybe 100 dimensionals. So what's the algorithm for that? And do you get my message here? Like, for example, this will be a really watered down example where you have this signal is in 2 dimensionals, right? But as you can see, like this signal is actually mostly fall in on along this line, right? So I can really project this signal just down to this one dimension. That's how the dimension reduction works, right? And you can imagine that if I have high dimension, it will be the same principle, right? So now if I have 10,000 dimensions, of course, even I fall down to like this 100 dimension, I cannot picture that, like I cannot visualize that. But it will be like a lot of shrink down of dimensions, like from this 100 or 10,000 dimension to 100 dimensions, right? So anyone remember that? Like half like so or so basically the standard algorithm to do that. There's lots of actually, if you look for literatures on dimension reductions, there will be lots of literature on that. But the simplest, the classic one, that again I guess is a good take-home message you should know is like the PCA, the principal component analysis. So okay, all these are just. So PCA is exactly doing this. You have this data here. You're trying to visualize. Basically, like they call it principal component. So it's the if you have this data set here, data points here. You have this data point here. So it have most variation along this dimension, this direction, right? The direction or the dimension that have like most variation, we call that the principal component. So that's why they call this a principal component analysis. So and PCA is a classic approach. So I'm not sure I have slides for explain PCA, but yeah, probably I didn't put anything here. But anyway, you can take it up. Like, or actually, I'm going to talk about that like in my next class. But here is like the training data here. the first thing is that we need to make sure all these faces should be aligned. So if you have the data points or data sets are not aligned, or like they will just behave differently, right? They have different statistics, then you cannot do dimension reduction for that. So therefore, PMUS for that, like, or you have some pre-processing here, you need to align the faces first, like before you're doing that. So therefore, like basically when you do have when you have this face recognition algorithm, you typically will hook that up with this face detection. Like for example, like Viola-Jone said earlier, right? It detects exactly where's the face. Maybe you have even like additional procedures just to align the face even better, like before you do the face recognition. So for the principal component analysis, for each of now you have each of these faces are 100 by 100 dimensions, right? So when you think of like we have this, let me go back to this one. When we have this 2D picture here, each of these dimension here along this direction here, that will correspond to some kind of phase also. Of course, along this line, if you increase the values, you will basically have phases have like larger intensities or like brighter. But if you just look at that direction there, like it will correspond to some phases, right? And that phases should be the phases that is most typical. In that case, would be the principal component. And actually, you can look at that, those principal components there. These are the first, I guess, is the 64 principal components. So you can see the variation of different phases. Like the first one probably is like more or less like mean, but change a little bit. But basically now you're using all these as bases now. So you have a new phase coming in, you will project to all these principal components, and then like the projected values will be your features. And this is just showing these principal components. I'm trying to visualize that like better by kind of like have a mean phase there that I'm trying to see like when we vary this mean phase by this principal component, how does it look like? For example, like for the first 8, this is 9 principal components here. If I increase the mean phase by like 3 times the variance, that you get like phases like this. And this is a minus 3 times the variance. And you can see like each of these principal components, they have this different emphasis, like in terms of projection. For example, like the first one, maybe it's like the color of the face, right? So more like the tone of the face. And then like maybe some of these, like for example, this may be related to the eyes. I don't know, you can see like when you increase that, it will be part of the nose also. Like if you look at the variation here, like the eyes is pretty obvious. Actually, many of them are probably related to eyes and so on. Anyway. And in terms of training, so first of all, of course, we need to align the images as I mentioned. Then typically you need to like subtract the mean first. This is a typical pre-processing step to just make sure your data is zero mean. And then afterward, actually you compute the covariance and then you diagonalize that. After you diagonalize the covariance, then you have the eigenvectors is basically your principal components. And there's also why they call it eigenface, because each of these principal components is essentially the eigenvectors of the covariance matrix. So then to visualize, as we earlier, we basically project the new phase to all these eigenvectors, right? So we have this new phase coming in, project to these eigenvectors to have this this projected values here, And then when we reconstruct the face, we have the mean face added with the weighted eigenfaces there, of course weighted by these projected values here. And of course, also like for classification, this will be basically your features, right? So for example, you have like 100 features, 100 eigenfaces. So you have 100 of these projected values. Then you have used this value and put it into an other classifier, typically SVM and so on. Then you can do the classification. So this is just illustration of how good you are doing the reconstruction. Oops, I don't have the K values here. I guess it's probably 100 or something. Then you only have like the first 100 value. Actually, think of that is kind of interesting, right? Because you have lots of information in this image here, but to reconstruct this image, I only need 100 values. And it will give you back this image. Of course, I have lots of assumption of this image. First, it's a face, right? It's a human face, not a dog face, right? So given all this assumption, and it's well aligned in this way, instead of like aligned in the sense it's like 100 by 100 pixels instead of like 25 by 25 pixels and so on. But given all this assumption, you only need like maybe like 100 values to describe your face there. And that's actually I have this actually have the K here. Probably they have more 100 than them in the early example, maybe 400 or something. But still, like you don't need a lot of values to create the face. And testing just go through the same procedure, right? You have the image coming in. Anyway, just repeat what I said earlier. So after we generate the features, we do the classifier. Here it suggests that even you can do like a simpler classifier than SVM. For example, like you can even use just K-list label. That basically means that, like, for example, I have Eunice face here, like he registered to this system here, then he compute these features, like maybe like 100 features here, like several of these faces, like maybe just one is enough. Then here's his new space coming in, we just compare this like 100 values features with his features. I just compute the distance there, Euclidean distance. They have this so-called Mahalalobos distance, essentially it's just Euclidean distance, but you scale that with the variance. So in the sense that you, if you have one of the features have larger variance, then you will count it smaller, right? Just basically weight your distance with the variance of that particular component. And that's also example trying to not just classify person, but you can classify the whether he's happy or sad and so on, so forth. This disgust face and surprise and so on and so forth. So that's some shortcoming here. It is not exactly real shortcoming, I would say, because most algorithms have the same problem, because you typically need to first do a good alignment before you have like good recognition. Even in deep learning, like it looks like you didn't do that, but actually probably the earlier layers did that already. So and also like because of that you need alignment, and also like you will be sensitive to scaling and also sensitive to angle. Right? If you tilt the face a little bit, probably it's not that accurate. Or like you need to first tilt your face back to have a good recognition. Of course, you can do some of this kind of workaround, like you trying to train across all different angles. I'm not sure this is a good idea, honestly. Probably a better idea is just to identify, okay, what's the angle of your face and try to tilt it back. Because you can have a reference face there. Let's say you know like all people, it looks like this angle, right? Then you can try to train the model to detect, okay, this is your face tilted with like 19 degrees. Oh no, 19 degrees is too much. Okay, 19 degrees is not too much. 90 degrees will be too much. So you can tilt it back, right? And then you do the recognition there. Okay, maybe one more thing I'd like to talk about. I still have time. Is like a real disadvantage or limitation of Eigenface is that like it's not actually it's optimized for reconstruction. You have this very efficient representation to reconstruct the face, and actually it's kind of optimum if you assume linear model here. But it's not optimum in terms of discrimination or in terms of like classifying like one face, like Joe's face from like maybe Unix face or whatever, or Travis face or whatever. So and the again like this is honestly I guess that's why like if you have a chance to take a machine learning class, it's really useful to take it, because many of these algorithms I mentioned here is actually just classic approaches like in machine learning or M statistics as well. Actually the standard way to do perfect, or I shouldn't say perfect, like optimum discrimination with a linear model is actually the linear discriminant analysis instead of like PCA. So therefore, immediately people try to do it, right, using like LDA there, and LDA, yeah, actually it's like it's basically appear in the same paper as well, like Eigenface and Fischer face, because like LDA is also known as like Fischer linear discriminant analysis. So therefore, like they also call it Fischer face there. So okay. Some high-level idea is like this. So you have, let's say this is again a data point of some faces here, and let's say this is a just somehow like again like this is a face space, but like this is like these two different dots are like faces of two different individuals here. And somehow, let's say if the principal components is along this direction here, so we're trying to project along this direction, right? But as in this example, the best way to discriminate, to kind of like distinguish like these two different individuals, should project the data along this axis instead, right? So if I have data point, if I project to here, basically this is bad. Like there's no way I can distinguish like these two classes here, right? But if I can project onto this axis, then immediately, okay, I can, okay, is that here? Is that here? I hope I didn't, yeah, lost anyone here. So when I mean projection, I basically like have this map to this axis here, right? And for example, like this point here, maybe this value is like, maybe this is origin here, this is 0, and this is 5, this is 7, and this is -2, and let's say, right? So if I have, in this case, after the projection, anything is my negative values will belongs to this, let's say, face B here, and anything is a positive value with face A here. On the other hand, if I project to here, there's no way, project to axis, this axis here, there's no way I can classify, like, maybe I can put a line here, somewhere here, but all these will be misclassified, right? I can say like all this belongs to A, like in this direction, everyone belongs to A, but all this will be misclassified now. And everything like on this side will belong to B, but then like, all these will be misclassified now. So so that's therefore like you see like PCA doesn't necessary to optimize in terms of like trying to distinguish like different classes. So LDA does this, but by basically with this simple idea here. So we try to see the again, like this is basically like illustrating the same example again, right? The same idea here. So this is good projection, this is bad projection here. And what we want to do is like, when we have, let's see if I can go to a, yeah, if I want to, what I want to do for a good projection is like, we want to have as large as possible this between class scattering, right? I want to have the mean of the two classes as far away as possible. And at the same time, I want to minimize this within class scattering as possible, right? So within one class, I want to minimize this variance as much as possible. So to do that, basically, is I have a kind of a formulation like this, where I want to maximize the between class scattering and minimize the within class scattering. I can just maximize the ratio between them. And then let's say I have two classes. Like this is class, this A and B here will be like, I have index like y is equal to 1 and y equal to 0 there. And this is just illustrating like if given y is equal to 1, what's the mean for these faces here, right? And this is y equal to 0, what's the mean of the faces there. And I want to compute the difference, basically the square of the difference of the means there. And then also like within class for the variance for given like is y equal to 1 minus y equal to 0. Let's see. Oh, wait a sec. Oh. Yes. Yeah, a little bit more detail here. So, let's say I have this. This will be the mean for the class 1, right? Mean for the class 0 here. And I just rewrite this as a mu 0 and mu 1 and mu 0 here. This is mu 1 and mu 0 is in the original space. And let's say I project it to that particular direction here. The projection is W here. Then I will try to, then the between class distance is just basically this projection multiplied by this mean here in high dimensional space, and then take the square, then rearranging the term, I will have this here. And then the within class variance, let's say just for the class I here, the variance will be, I have this expectation C minus the mean here, so it's like this expectation x minus this mu I given this y equal to I here. So I have these terms that are very similar. And then you see this projection here, I can actually pull it out in the expectation here. If I pull it out, the thing inside here is just the variance of that class. So therefore I have the variance is just equal to this guy here. So then the two terms we have earlier will be just the ratio here will becomes this projection W multiplied by this SB and W. This SB will be that we have earlier is just the square of the means there. And note that this is a matrix actually, because this is a column vector, this is a row vector, right? This is a matrix here. And of course this covariance also like matrices here. So and then we have basically this term here. Now, yeah, this is just visualization. Now, I have a formulation like this, right? So I have, originally I say we're trying to maximize this here. But I can also do it this way. I can say, let's keep the within class variance to be fixed with some values. And then I just trying to maximize the across class distance there. And so then I will have a optimization function, optimization problem like this. And do you know how to solve this? So it's kind of like, okay, optimization problem. This is just a scalar function, right? But this, you have this W is a vector here. So, but the problem is I have this constraint here, right? I have a constraint. It's a constraint optimization problem instead of like unconstrained optimization problem that I think like most of you learned that like in calculus class, something like if you have a kind of unconstrained optimization problem, if I have a vector variable here, so we were just trying to compute the gradient, right? You're trying to compute the gradient of that guy here and set it to 0. So then we'll give you the extremum, right? Either the maximum or the minimum there, right? So, but now I have a constraint here. I've constrained this guy here. So recall you see anything like this, like in any. So again, like this is a very common problem, like in engineering and everywhere, that like you don't just like get into like unconstrained optimization problem, but sometimes you have some constraint there, and standard approach is using so-called Lagrange multiplier. Now, anyone recall anything? I heard of that, Lagrange multiplier. The Lagrange multiplier is trying to absorb your constraint into the original objective function there. So now instead of like trying to optimize these guys, you have a new objective function that with the constraint absorbed into that. And then again, you can just, like you have an unconstrained optimization problem, you're just trying to take the gradient of this guy and set it to 0 and find a solution there. I won't go into detail of this because yeah, I guess it's very good to know because this just occurs everywhere in engineering problem. So just do that. Like we have this Lagrange multiplier problem. Now I take the gradient over this new objective function, and then I basically get simply get this. I have this SBW is equal to this guy here. So it is something known as a generalized eigenvalue problem because I have two matrices. It's not like the original eigenvalue problem. That basically, if I don't have this guy, it's just original eigenvalue problem here, right? But now I have SW here. It's a little bit different, but still is. If this SW, if it's like if invertible, then it will be easy, right? But in most cases, it will be invertible because SW is just a covariance matrix. It's typically is kind of like positive definite. So I can invert that. So then it will just move to the other side. So it will be SW like this. Then I can just do a eigenvalue decomposition for this guy now. And then SB, I can rewrite this back into this. I know this is this guy originally. And another observation is that, like, again, this is a column vector here, this is a row vector here, this is a row vector here. So this guy is actually a scalar, right? This is a column vector again. So this is actually a scalar. So therefore, I can just call it something like maybe I call it alpha here. I can put it on the other side. Then what I have is something like this. This is equal to this guy here. So therefore, like W star, if I don't care about the scaling factor here, I have the optimum W is essentially just this guy then. So therefore, like has a very neat result here. It's very simple, actually, the final result. And for multiple classes, it's more or less the same. I won't go through that. So basically, again, just construct the within class scattering and between class scattering. Then you just go for the same optimization problem, right? And then essentially you can, again, I just solve this generalized eigenvalue problems. In this case, you may not have as neat result as we have earlier, but you can just move this on the other side and eigenvalue decomposition for that and to get that W. So and for earlier, like actually as you can see, I thought like I need to do an eigenvalue decomposition, but I don't need to even for the earlier. You can write down the solution right away. And so in terms of Eigenface and Fischer phase, Fischer phase is actually optimum to do this classification. At least with the linear model. So and this is just like basically the original setup of the setup of the original paper. They try like different conditions like without gases. They train like it's not a very large data set, like only 160 images, like 16 people and so on. So Fischer phase, they got like 7.3%. Okay, of course it's not really that much now, but I guess I like to mention this because this both PCA and LDA like kind of classic algorithms that used in many places. So and they are useful not just for like face recognition. You can just create exactly the same kind of recognition algorithms for anything. For example, if you have like vehicle recognition, let's say just car, the first thing you can exactly use the same idea as Eigenface or Fischer phase here. If I want to classify a truck from my car, let's say, I can just first have a detection, detect the car here, and then I just need to align it well. Then I can just do exactly the same procedure that kind of prepare my data set with all the aligned images. Then I train them. First, I do the dimension reduction with like either PCA or LDA, and then with this feature, and then go through either K-Lewis label classifier or like SVM and so on. And that gives you a kind of decent result actually, like for many applications. And I guess that's all I have today. So my timing is good today. So okay, I'll see you guys Thursday.